Welcome back, everybody. We are going to talk about benzyl alcohol. Mainly benzyl compounds really would have a similar pattern. So this is a good one to get to know. Besides, a lot of the things that have benzenes have similar patterns. So let's look at one. So you can kind of extrapolate to the others and figure out what's going on with the fragmentation patterns. Shall we? Okay, let's look at this. Your molecular ion peak is 108. So here is the possibility for that. You have your electron ionization, high-speed electrons impinge on that, take it out, and you are going to have a molecular ion peak at 108. So the molecular weight for this is 108, and so if you have a CH2OH, so that got taken out, there's a hole in there, and that is your 108 molecular ion peak. Well, 107's next. It's pretty tall, so we really can't ignore it. That's just one, and there's only one thing that can have a weight loss of 1, and that 1 is the hydrogen, right? So you know that. So let's look at that. So here, there are some possibilities for this, but if you have a benzene with a CH-OH and you have a positive charge on the oxygen, it's going to want to try to pull electrons toward it. It can pull all of these, but let's see what happens if it pulls this electron over. And that is going to give you a double bond right there. And that double bond is going to have a hydrogen and a lone pair. And if you look at the formal charge of that, that's going to have 1, 2, 3, 4, 5, and you're missing 1. So you have a whole positive charge there. So that's just for formal charge. 6 minus 5 is 1. And then your hydrogen just leaves. They don't want me, I'm getting out of here. The radical's gone. Well, what do we do with a 107 now? So this is a 107. Well, one of the things that you could think of this molecule doing is kind of expanding into this. And, well, they don't really talk about, like a rearrangement going over there. And that could give you a tropylium here, which means a 7-membered ring, and let's say this kind of expands out there. That's just going to give you that. So over here you still have a positive, and that's going to be here. So, well, the positive due to resonance can move around, and you can write this out as a tropylium cation, hydroxyl ion. That's your 107. Let's look at B. Well, let's look at another possibility. 108 going to 91, that's 17 missing from here, and so that 17 is going to be, if you think about it, water is 18. So what do you think a 17 is? Just one proton short of water. So that's a hydroxyl. And you can see how this hydroxyl can get out. And you see this all the time in mass specs, this 91 peak, when you have benzene compounds with side chains, alkyl side chains. So here is your CH2OH. And again, I'm going to just draw the molecular ion here. And here, the hydroxyl wants to leave, and you can have a heterolytic cleavage here, which means both electrons go over and give you a benzyl cation. Now, benzyl cations are pretty good because you know that you can draw all kinds of resonance in here with this molecule. Well, let me see, like that. It's pretty stable because your positive charge is smeared all over the molecule, all your charge. Now, what could happen with this? Well, once you get to this point and you have your hydroxyl, which is now going to have one electron here and 2 electrons for a lone pair, so that is going to be a 17 hydroxyl radical, nasty things that really make your food spoil and do all kinds of things. But it's okay, this is in the mass spec, so let's not worry about what hydroxyl can do right now. Let's think about what this guy can do. This is your 91, but if you take an NMR off this peak, there's only one peak. So, and this would definitely have more than one peak, bigger type of hydrogen. So I guess you haven't done NMR yet, but you only have one type of hydrogen in the molecule. So think of this as expanding into here. And that could give you a possibility for this molecule to actually look like this. So this is your tropylium cation. And your positive charge, instead of just being on one carbon, is spread, and that is an aromatic molecule. So this is aromatic, that means it's extra strong, extra stable, and 6 electrons, cyclic, and so on, which you're going to look at. This is extremely stable. It's like benzene's aromatic. This one's also pretty stable. So that's your 91, and you would see 91, in a lot of molecules. Let's look at what a 79 could look like. 79, or actually, let's look at 77. So this is going to be 77. You can think of having a benzene here, and you can think of this benzene actually just having a heterolytic cleavage right here to give you a phenyl cation. So that is a possibility for that. So this is your benzylic radical, the same molecular ion peak at 108. Let's see what we can do with that. You can think of this kind of having a heterolytic cleavage here and going over there. And that could give you a 77. But that's, and you've seen, that's one possibility. And so this is just going to go over here and make that into a neutral alcohol, H, and that radical just goes away. This could be 77. Another possibility is this cation here, the tropylium cation, just spitting out a CH2 and going into a molecule like this. And most of the books really don't dwell on the mechanism, and it's complicated, but this is kind of what it would look like. 2 hydrogens here on this benzene, and all of these would have hydrogen. So this is kind of benzene with an extra hydrogen here. So you have 5, 6, 7 here, hydrogens. 72 is for the carbons, and so we can just draw it like that. That's your 79 peak. And 2 of the hydrogens can go away, give you an extra double bond there, and that is going to give you a 77. So that's 2 ways of doing it, and this is typically what you would see most of the time. Now, what's for 51 and 39? Well, that's another pathway that most people propose when you have a phenyl cation. Over here, you can think of this as having these electrons then rearrange. So these electrons, you can think of it as something like this. So you have a 4-membered ring with a cation. I know these look pretty bad, but that's what's proposed. And the only way to tell is to get an NMR. This is 51. There have been some structures here that's been suggested for 39. And so even though, I mean, this may be actually a little better than that, and that could be a possibility for that. So these are some of the ways in which benzylic compounds have fragmentation inside the mass spec, and this is fairly typical. Making an expansion to these 7-membered rings or tropylium ions, and also having, a contraction of the rings. So in summary, I'd like to say that benzylic compounds would fragment in a certain pattern, and the most stable fragment of all of them is really the molecular ion peak here in this case. That may not be true all of the time, especially when you have aliphatic alcohols. You hardly see the molecular ion peak, but here the molecular ion peak is really strong. Now, if you take the molecular ion peak, if you take off a hydrogen, you can see how you can get this fragment over here, and that can then expand into this tropylium alcohol. That's about a 107 over here. The reason for that is you can see this can have a lot of resonance by running around the ring. Now another possibility is losing that hydroxyl 17 and then having that benzyl cation, which is already resonance stabilized, become even more stable by expanding into this tropylium cation at 91. Now that 91 tropylium cation can then fragment into these other pieces by giving up carbon fragments. So from here, it can go over here by spitting out a carbon, and the 79 then can give up 2 hydrogens and become a 77 peak here, like a phenyl cation. That cation can then contract some more and become a 51 cation here with a 4-membered ring. And they have also suggested for 39 a cation, a propyl, cyclopropyl cation. So those are some of the possibilities that you would see in a typical benzyl cation pattern. You would see a lot of the mass specs that have any benzyl group here. It could be an NH2 or something else. You would see these fragments. So what we're seeing is really trends for these molecules in mass spec. Talk to you soon. Bye.